So from the Darwinian's concept, you should create a natural selection. That particular natural selection should help you to select automatically rather than human inversion without any bias. For that, there are a lot of selection mechanism available in evolutionary computation, including genetic algorithm. Here we have something called a roulette wheel, where we have something called a pie chart. We will allocate proportionate area for each of the chromosome. For example, the chromosome 4, which is having higher fitness value, we are providing more area. The chromosome which is having lesser fitness value, that is individual 3, we are providing lesser area. Right? Then we try to rotate this wheel and suddenly stop. We will have a pointer. Most of the time we will have a pointer, and this pointer will be always pointing it to a location. When we try to rotate and stop suddenly, this pointer will point to a location. Whatever location this point, that individual will select in the new generation. So we will repeatedly do several number of times depending upon the number of chromosomes that we need. Each time we will rotate it and stop suddenly, and the pointer will point to a location. Wherever the pointer is pointing, that particular individual we will take for the next generation. So what the probability theory or statistics theory tells that those chromosomes that are having more span of area will be selected more number of times in the next generation. That is the possibility of a chromosome that is going to be available in the next generation depends upon the span of area that you are having on the pie chart. If you are having more span of area, you will get more number of times selected. And if you are having less span of area, you will have less number of times selected. Right? This is how it happens. Why this is needed is that in a classroom situation, if some students are there, if one of the student is failing in one subject regularly, right? What the industry will say that this particular student is not suitable because he is having arrears. But there is another way of looking at him. Why he is failing on that particular subject, whether he is having good capability in some other subjects. Suppose he is continuously failing in a language subject, suppose English, right? Or some other subjects like interdisciplinary subject, but he is having very good marks in computational aspects, physics and other bioinformatics or something like that. We can understand that he is having skills in certain domains. So the industry should not simply quit him, right? Rather than we have to take him and understand that he is having some good genes and try to utilize him. That is why most of the time failures, even if you take any scientist example, most of the scientists, if you take, they are failures in subject, but they have found out some of the novel things in the world, right? So we should understand, we should not throw away certain chromosomes which are very weak. For example, this chromosome is very weak, but we should not throw away by manually. We should allow it to natural selection like roulette wheel, which automatically select based on the probability theory. So this is how the selection mechanism works. Then we have crossover. In the crossover, we have a parent chromosome. We will have a another parent chromosome. We have a random crossover point. This crossover point will be selected randomly, not manually. We'll have a random function to do that, and then try to exchange the values between those things. Right? So this portion comes here, and this portion comes here. And this becomes something called offspring chromosomes. So this is how we do crossover. Here the crossover point will be randomly selected. This is the example of 1-point crossover. You have 2-point crossover, you have multi-point crossover, you have shuffle crossover. There are several types of crossovers are available. You have to select one of the type of crossover and do the crossover. So the crossover points are randomly selected and you try to exchange, because as I have already explained that certain genes will be very good in certain chromosomes, certain genes will be very bad. Due to the availability of bad genes, the performance of the entire chromosome will be less. We will be thinking that chromosome is very bad. We should not throw it away, because some of the parts of that chromosome, that is some of the genes, will be very good. We should utilize it. So this crossover functions will help you to achieve that. Right? We try to cross over between the genes, and certain times the good genes will combine together to get a higher fitness chromosome. That is how we do this particular task. Right? Then the third function is called mutation. Mutation will take a chromosome, if it is a binary chromosome, randomly we'll select a crossover mutation point, and we try to change the value. If it is 1, we will make it 0. If it is 0, we will make it 1. If it is a real valued chromosome, it's randomly select the mutation point and try to increment or decrement the value. Either increment or decrement the value slightly. That is mutation. So all the functions in the genetic algorithm are over. One, we have talked about selection, that is over, very simple. A probability roulette wheel making is very simple. And second one, crossover, randomly making crossover points and exchanging the values, very simple. And mutation, randomly taking certain points and changing the values, that is also. So these are the three very simple three functions that is being utilized in genetic algorithm to do optimization. So I think we can just see an example in Matlab. I have a small example that I want to show you. So I have a toolbox. This toolbox I will share with the organizers. This toolbox can be used for the purpose of genetic algorithm. There are in Matlab there is another toolbox available. So any one of the toolbox you can use it, but you have to familiarize with the functionalities available. This is one of the toolbox that is called GEATBX. There are a lot of functions available in that. The only thing you want to do is you have to take this particular folder and place somewhere that you are going to any place you can place that. And in the Matlab, what you want to, I think two Matlabs are open. So in the Matlab, what you want to do is you have to add to the path. You can see the set path here. And the set path, you have to add the folder. Add the folder. And you can take that GA. And this entire folder I will provide to you so that you can make experiments. So this you have to add it to the set path, because all the functionals will automatically come to the path, and you just save this. So this initial thing that you want to do that, so that you will be able to utilize this particular toolbox. Now coming to the program, I have a small code with me. I think I have a small code that will help you to understand sorry. Yeah. So we will see step by step from here. Those who are those who already know Matlab, it will be easy for them. Otherwise, I will just explain quickly, right? So this CLC is just for clearing the workspace and clearing the screen. For these two things we use for that, right? Just initially, so that if some other values are there on the workspace, we want to clear it just for that particular format. Thing. And this format compact normally we use so that we can avoid the space. Certain times, certain Matlab will have space between two lines that is being displayed. In order to minimize that, we normally use that format compact. And as I have already told that when you try to create a genetic algorithm, you need to have something called a population. A population will have so many chromosomes. How many chromosomes you want? That is being defined by a variable number of chromosomes. So here what I am defining, I want 50 chromosomes, right? Each chromosome will be a solution, may not be optimal one. And as I told that in genetic algorithm, we will do the things several number of generation. The first time we will go to selection, crossover, mutation, then evaluate it. Then we will check whether optimization has been reached or not. If not reached, then again second generation. The second generation also selection, crossover, mutation. Like that, several number of times you will rotate until you will get the optimal solution. And this number of generation, here I have used a variable called maxgen, which is 500 number of generation. And we have something called crossover rate. So when you take two parent chromosome and select a crossover point and do something called exchange of genes. So this has to be done not for all the pairs of chromosomes. We have to have some probability. 80% of the chromosomes will undergo crossover. Remaining 20% will never undergo crossover. So we can define how much percentage of the chromosome should undergo crossover. So this can be defined by a probability called crossover rate. Similarly, mutation rate is there. If you take a chromosome, how many genes should undergo changes? We have selected random crossover mutation points and try to change values, right? How many percentage of the genes should be selected, and so that it can change? Because if you do more mutation, if you have more mutation rate, the entire chromosome will get damaged. So small mutation. That is why even if you see the natural evolution, slight changes happens, right? Next generation will come slight changes, right? So that is why the evolution happens. Suddenly a coconut tree is not becoming some other tree. Suddenly a dog is not becoming some other animal, right? Suddenly a creature is not becoming a new creature. So slow changes happens, right? Slow changes happen. So mutation should be very slow so that it will never disturb the flow of optimization. So we have a mutation rate as very less, that is 0.01. And then we will start with initial population, that is generation. We have a variable to store the initial generation value, generation 1. And there is a function called init BP. This init BP will help you to create initial generation of population, right, with random values. As I already told, in the genetic algorithm or any natural inspired algorithm, human beings will not have a direct influence on the algorithm, right? It should generate randomly. So initially it should come naturally to a optimal point. So this init BP, we will see what it will do, right? I will take this command prompt and I will show you that what this init BP is doing, right? So this init BP, if you take it and put it here, and you have something called help file where you put this init BP, and you see that it will show the what this init BP is actually doing, right? Init BP is creating an initial binary population, and it is having something called a number of chromosomes that you want, and the length of each chromosome that you want. That is what it is asking. If you just put help, it will provide you the details. And let us see that how this init BP works. So I want 5 chromosomes. I'm putting 5, and each chromosome should have a length of 10. This init BP means binary population. Automatically, it will create a 5 random chromosomes, right? This is the first chromosome with 10 individuals, 10 genes, binary genes. And this is the second chromosome with random 10 bits. And this is the third chromosome. Like that, you can specify how many chromosomes you want, and each chromosome how many bits you count. So within a single statement, you can write your own function for initialization, right? This is available in the GEA-TBX, this folder that I will share with the organizer, so they will provide to you. And where you provide the number of chromosomes that you want and the number of bits that you want. So once you give that, when you call this function, you get automatically the population. So creating an initial population is easy just by having the single statement, right? That is how this statement is been here, right? What I have mentioned here is number of chromosomes that we have already mentioned 50 earlier, and this is the number of bits that you want, right? If you want 400 bits, you can mention it as 400, length of the chromosome, right? You can mention it here. You will be able to create the entire population, POP you will get. Once you get the initial population, the next step is to evaluate each of the chromosomes, I have already told you. Now this example is nothing but a smaller example so that you will be able to understand it much clearly. It is a 1-max problem. This problem is a 1-max problem. The problem is to maximize the number of ones on the chromosome. So what will be the fitness value? If you say that the fitness value of a 1-max problem is the count of the number of ones, right? If you take a different problem, the fitness value will be different, fitness function will be different. Here, since it is a 1-max problem, the fitness function will be nothing but the count of number of ones. So what we want to do, just add the number of ones there in the chromosome. You will get the fitness value of a chromosome. Right? So here what I have done is just have a sum of the entire population. Right? Since we have this transpose, because most of the time when you put sum of a matrix, it will try to find out the sum of vertical columns. Since we want to find out the sum of each chromosome, we want to transpose it so that we will get the sum of number of ones available in each of the chromosomes. That is why we are having this transpose. Those who are already doing in Matlab will know this. Right? So we will see this, how this happens. So for example, you have init pp here. I am trying to store it in a population. Assume that this is the population that you are having. Right? I want to see that 1, 2, 3, 4. This is the fitness value. 4 is the fitness value of the first chromosome. 1, 2, 3, 4, 5, 6 is the fitness value of the second chromosome. That is what I want to know, right? So what I do, I have something called a fitness variable where I try to find out what is called as sum of all the chromosomes, right? You can see this is 1, 2, 3, 4, right? You can see the fitness value is 4. The last one we will see 1, 2, 3, 4. You can see 4. Right? The middle one we will see 1, 2, 3, 4, 5, 6, 7. You are able to get 7. Right? So you will be able to find out the fitness value based on the problem. So if you have a problem, different problem, you have to write your own fitness function. Since it's a 1-max problem, easy to find, just add ones. Right? You can create any type of fitness function. It is the duty of the designer to design a fitness function. Right? So now after finding the fitness function, these portions are just used to store each generation. It will create a maximum fitness, right? We want to plot it. So in order that I am trying to find out the maximum fitness from all the chromosomes, right? Some of the chromosomes may exhibit a maximum fitness that I am storing in a variable so that I can plot each time. And the chromosome which has been exhibiting maximum fitness value. One of the chromosome may be exhibiting maximum fitness value. That chromosome I should store it in future so that I can understand in the first generation which chromosome was showing maximum fitness. In the second generation, which chromosome was showing maximum fitness, I want to know. For that, I am storing that in again a variable, right? This index I am taking it so that I will get a chromosome which is showing the maximum fitness value. I am storing it a variable called maxchrom. I can use it in a future reference, right? Then I am plotting it each time, each iteration I am trying to plot it, and this delay is just to make certain times Matlab is very fast and it makes certain delay to display the screen. So you will feel that Matlab is stuck. In order to just avoid that, I am just having a pass statement that is not at all needed, but you can include it so that when you try to do something, it will be visible to you without any problem, right? Then this has been run, right? You have a while loop, right? This while loop will run entirely for 500 number of generations. I already told that you will run it for 500 number of generations. So initially what we have done, we have created a random population. We have a fitness function. Using the fitness function, we have calculated the initial fitness value. Then we are inside the loop, right? We want to do selection, crossover, and mutation. So for genetic algorithm, we are having this toolbox supports several types of selection functions. One of the selection function we call it as cell RWS. That is called Rowlett wheel selection that we have seen earlier. In this Rowlett wheel selection, you have to provide the fitness value that you have obtained. And after providing the fitness value, how many chromosomes you want to select, that also you want to give. So we will see this, right? If you have this function, this is already available in that particular toolbox. You take it and do what is called as help. Help, you see that it will provide what are the things that it will do, right? It is a Rowlett wheel selection function and it has to give some fitness value and you have to provide how many chromosomes has to be selected. So here what you can see that I have given here a fitness transpose, because earlier we have seen that fitness is horizontally, it's a row. So we want to make it column. So I have provided fitness transpose and provided the number of chromosomes. Let us see this example, right? So we have created a population, right? And we have found out a fitness, right? This is the fitness. And what we are now going to do is cell RWS, right? Cell RWS, and see that how this works. So fitness transpose, and I want to select 5 chromosomes, right? I want to select 5 chromosomes. See, now very interestingly, we can see that this is the index of the chromosomes, right? 5th chromosome is selected one number of time. The first, second, third, fourth, and fifth. 5th chromosome is having a fitness value 5, that is being selected one number of time, right? And you can see that the second chromosome that is selected 3 number of times. You can see that second chromosome is selected 3 number of times. Why? It is having a higher fitness value. You can see 7 is the second chromosome is having higher fitness value. As I already told that this is random. So Rowlett wheel is able to decide based on random values. So automatically by natural way, it will be selected without any human intervention. Next time when you execute the Rowlett wheel, you will get a different value. For example, if I am trying to execute the second time, you will get a different value. Right. So this in the first case, you are seeing that second chromosome is selected more number of times, and the first chromosome is selected one number of time, and this chromosome is not at all selected. Fourth chromosome is not at all selected, and the third chromosome is not at all selected. So we are allowing the naturalism there. So let it select it on based on random values without any human bias. Second time when you execute, you can see that the fourth chromosome is been selected one number of time. The third chromosome is selected 3 number of times. The second chromosome is selected one number of time. Right? That's it how the cell RWS works. So different times it will work based on random values. Now we will again go to the problem. The selection is over. One of the very simplest function is over. Just you can write your own selection function, or you can use this function. And now crossover comes. There are various types of crossover function available in this toolbox. One of that particular crossover is something called shuffle crossover. Shuffle crossover means it initially shuffles the genes between it and then have some random crossover points and exchange the genes between 2 chromosomes. Here we want to provide the entire population after selection has been done. Then we want to provide the crossover rate. How many percentage of the chromosomes should undergo crossover? That we ought to provide it here. So this is XOVSH, that is shuffle crossover. So let us see that how XOVSH help. You just have something called help XOVSH, right? So this will this will provide something called crossover, shuffle crossover. In order to understand it very clearly, let us have a demo of single point crossover, right? That will help you to understand much clearly. So shuffle means since it is shuffling, you will be feeling very difficult to understand. XOV SP, single point crossover. So in single point crossover, you can see the all the chromosome we have to provide and the crossover rate we want to provide. So let us take the same example. We created a population with a random population with 5 chromosomes and 10 number of genes, and we try to evaluate it with that fitness value, and then we do something called selection, right? We do something called a selection. Selected population we will write, and that selected population is cell RWS. We will provide the fitness transpose and the corresponding number of chromosomes that you want to select. Right after finding the selected, this is index, right? So the new pop will be nothing but the old population with this index, right? This index we have to provide to it. This index we have to provide to it, so that we will get something called the new population, selected number of population. From this new population, now what we are going to do, XOVDP, right? This is the thing we are having. Now what we do, XOV DP, right? Crossover with single point crossover, SOV XP, single point crossover. Here we give the population and also the crossover rate. For example, I am going to give crossover rate as 0.8. And you can see that this is the first chromosome, right? So you can see 1, 1, 1, 1, 1. But here you can see that 1, 1 here. After that, you are not able to see 1 here, right? right? Which gene we will see? We will take the second chromosome. Here initially we are having one here and one here. Here also we are getting one here and one here, but this value has been changed. This 0, this one has been changed to 0 because earlier this chromosome is having 0. This gene has been exchanged here. So these two genes, whatever you are seeing, has been exchanged. This one has come down and 0 has gone up. Similarly, these two chromosomes we take, right? This thing 1 1 1 1 1. See, you can see 1 1. Here two values, right? So several places you can see the exchange has been happened, right? So here this 0 has become 1 and this 1 has become 0, right? Here also you are able to see two places, right? No, one place here you are able to see one. So like that, it will automatically try to exchange the genes between the chromosomes. So you can write your own program for crossover, single point. This is whatever we are showing is a single point. You can have double point crossover. All the functions are similar. You have to just give the population and the crossover rate. That's all. Right? Very simple functions. These are things. And the third thing is something called mutation. We have talked about selection. We have talked about crossover. Now it is the third one is mutation. Once mutation is over, everything is over. Entire genetic algorithm is over. So how this mutation BINT will work? If you want to know more about it, you can have help. After putting that thing in path, you have a help function. It will show that what are the parameters it will take and what it is. It's binary mutation, right? You can have real valued mutation also. So here you have to give the chromosome, and if it is a binary mutation, this value will be empty. Otherwise, you have to range. You have to give the range. What each of the gene will have its own domain. You have to give the domain so that mutation will not create a value much greater than the minimum value and much lesser than the minimum value and much greater than the maximum value. So it will be between that particular domain. And this is the mutation rate that we want to provide. So let us see a small example so that how it will work. We will take a population and we will try to provide a mutation rate of higher mutation rate so that you will be able to understand it more clearly. Mute BNT, and we are going to give this population, and this value is empty. And since we are not going to have real valued mutation, we are going to give 0 there. And then mutation rate. Let us give a mutation rate of 0.5, something like that. Let us see how it works. So you can see that this 1 has been changed to 0, right? This 0 has been, because high mutation rate is there. If you give less mutation rate, the value will be different, right? So this one we will see, right? So 0, 0. Here you can see 1, 1, and this 1 has been changed to 0, right? And remaining things all are same. But if you give high mutation rate, you can see that this 0 has been changed to 1. This 1 has been changed to 0, right? And again, these two 1s has been changed to 0, 0, right? These two 0, 0s has been changed to 1. If you give high mutation rate, most of the values will get changed. That is not, we don't want those things. So most of the time mutation rate will be very less, so that only very less number of mutations get genes get changed. So these are the very simple 3 functions available. You will be able to write your own functions for doing selection, your own functions for crossover, your own function for mutation, or whatever has been defined by this toolbox or some other toolbox that is already available in the Matlab. Every programming language provide a toolbox. Java, you will get a genetic algorithm toolbox. In C, you can get genetic algorithm toolbox. In R, you can get genetic algorithm toolbox. In some other languages also you will get. So any toolbox you have to get and try to understand what are the functionalities. You try to write your own functionality or you make use of that functionality. So only these 3 things makes the entire genetic algorithm. And these portions are just to store the values that I have already explained, right? I want to store the maximum fitness that has been obtained. I want to maintain the chromosome which had exhibited the maximum fitness value. That I am just having a if condition to store that. That you can understand that is a if condition to store those things. And I am just trying to print it. What is the current generation and what is the fitness that you have obtained in that particular generation. And there is something called a reinsertion function available. Why we do is that due to selection, these are all random. Selection is random, crossover is random, mutation is random. Due to selection, crossover and mutation, it may so happen that some of the good chromosomes you will lose. You know that when you try to do some examination, even Viva voice, right, for a project for the students, we know that certain good students will get very less mark. And we have to certain times explain to the external examiner that this student is the class topper for the last several semesters. He has done something good. Because of the 20 minutes presentation, the external examiner might not have clearly understood that this student is good. So sometimes we have to inform, right? So similar thing here also, selection, crossover and mutation certain times selection may certain times because of randomness, it may miss the good chromosome to be selected for the next generation. Due to crossover, certain times certain good chromosomes may become bad. Due to mutation also, certain good chromosomes may bad. So we want to retain some of the good chromosomes from the previous population, the current population. For that, we have a reinsertion. Certain percentage you can give. Whether you want to have 50% of the old population to be taken as it is in the new population, or you want to have only 10% to be taken as it is, or you want to have only one chromosome to be taken from the old population to new population, that you can define. So I have made only 50%. I have made 50% of the old population to come to the new generation. So this function is also available in that. You can either use it or you can avoid that. And this is entirely, it will run for 500 generations. We will run it and see, right? I will just run this program. I will just try to run this program. When you try to run this program, it will keep on running, right? So you have something called, one more time I will run, right? You can see the fitness function keep on growing. This is a 1max program. I have already told that what we want is 1 bit, right? Once in all bit positions. It means that the chromosome will become optimal when we have 1 in all positions randomly. So since we are having 400 bits, you can see that approximately at the time when we are having 350 generation, we got something called 400 bits, fitness value something equivalent to 400. One more time you can run and see what it happens. See, so almost when it comes to 250, 300, right? You can see that we have reached 400 all once, right? It is doing randomly. We are not having any human intervention on this, and everything has been done randomly. What we have done, we are having selection, crossover and mutation. This helps us to do this particular task. Now, based on these few things, one more thing I would like to show you, that is a very interesting thing. Based on that genetic algorithm part, we will stop. Then we will move to fuzzy and other things. I hope that I can open this on Google Chrome. This is something called an experiment that will help you to understand, right? I will show you that. Before that, we will finish this. So here we are creating an initial population. I told that very simple. Randomly, you have to generate some random values. It will become initial population, number of chromosomes. You should have a fitness value. The fitness value will be different for each of the problem. It is the duty of the designer to design based on the problem. Then we have something called, we want to check whether the optimization has been reached or not, that we have to do it. Then the 3 functions, selection, crossover and mutation, very simple functions. You do it and run this for n number of times, n number of generation, you will get the solution. And this is how GA works, right? GA is very, very simple one. And you should not feel that it is very difficult. Similarly, all evolutionary algorithms, right? This genetic algorithm is flavor of evolutionary computation. All evolutionary computations, right, will have random values. No human intervention will be there. Certain times we can have human intervention also, but most of the time it will be done randomly based on some random values. You take nature-inspired algorithm like particle sum optimization, anti-colony optimization, bee colony optimization, Firefly algorithm. Everywhere, when you take any nature-inspired algorithm, this evolutionary computation genetic algorithm also fall under the category. All these nature-inspired algorithms and evolutionary computation genetic algorithm all used for optimization for any machine learning algorithms. can be used for machine learning algorithms or optimization. And all these things will have random values inside that. It does automatically the things optimization. So that is the beauty of these things.